Welcome everybody to the Chairman's Seminar here today. We're hosting Roger Atkinson and Janet Airy from University of California, Riverside. And we'll have two seminars back-to-back, a double header as we call it. And the first one will be by Janet Airy, who I'll introduce. Let me mention before we start that this is being webcast, and we encourage people who are participating via webcast to send in any questions that you have. We'll get them here and ask the presenters. And send it to coastalroom@calipa.ca.gov. So that's COASTALRM, one word, coastal RM, at Calipa, CALEPA, at ca.gov. Janet Airy is a professor of atmospheric chemistry at the Air Pollution Research Center at UC Riverside. Based on her research identifying the products of atmospheric reactions of volatile organic compounds, and particularly of polycyclic aromatic hydrocarbons, or PAHs, she was named as a Fellow of the American Association for the Advancement of Science, or AAAS. She has used smog chambers, or environmental chambers more properly, to simulate the atmospherically important reactions of organic compounds of both anthropogenic and biogenic origin, like terpenes. She's done a lot of work for ARB over the years. Most notably for me is the work in which she's found that atmospheric reactions convert PAHs to highly mutagenic products. And today we'll hear about her recent work on quinones. Thank you, Janet.
Thank you, Ralph, for that introduction. Good afternoon. Thanks for inviting me up here to talk to you about our contract polycyclic aromatic hydrocarbon sources of ambient quinones. First of all, why are we interested in quinones? Well, we're interested in quinones because of the potential health impacts. Quinones can have both acute health effects and chronic health effects. For example, quinones may covalently bind to proteins or DNA, so you can have a chronic health endpoint such as cancer. But quinones can also undergo redox cycling with their semiquinones, leading to the formation of ROS, reactive oxygen species. So in this way, because it's a cyclic reaction, you can produce one quinone molecule can theoretically produce many hydroxyl radicals. And the reactive oxygen species have been some of the acute health effects of diesel exhaust particles have been attributed to the reactive oxygen species. The atmospheric formation of nitro PAHs and PAH-quinones, and why I've included nitro PAHs here will be apparent in a minute. So PAHs can be in the gas phase, or they can be particle associated. If they're in the gas phase, they can react during the daytime with the hydroxyl radical, or during the nighttime with the nitrate radical. And both of these will produce nitro PAHs, the nitrate radical reaction producing higher yields than the hydroxyl radical reaction. For particle-associated PAHs, they could potentially photolyze, react with ozone or NO2 and nitric acid. The latter could form nitro PAHs, but if you form nitro PAHs this way, they're going to be the electrophilic nitration products of the PAHs, so they're going to be different from the ones formed by these radical reactions over here. Quinones can similarly be formed directly from the PAH reacting with the hydroxyl radical during the daytime, or with the nitrate radical at nighttime. We had shown that with naphthalene prior to this contract. In terms of particle-associated PAHs forming quinones, back in the 1980s, Jim Pitts was putting BAP on filters and exposing it to ozone and finding BAP quinones. So that's certainly one source people thought could be for quinones. And finally, nitro PAHs can photolyze to form quinones. So this is why we're interested in the nitro PAHs, because if you make a significant amount of nitro PAHs, if they photolyze, then you can end up with quinones. Sources of ambient quinones, they come from direct emissions. So for example, in diesel exhaust, 1,2-naphthylquinone has been seen, as well as 9,10-phenanthrene quinone. The atmospheric formation from radical-initiated to gas phase reactions that I just mentioned. Photolysis of the nitro PAHs. Here we see 2-methyl-1-nitro-naphthalene photolysing to form 2-methyl-1,4-naphthylquinone. and heterogeneous reactions such as with ozone, such as BAP going to BAP-quinones. For this contract, we were interested in the gas phase atmospheric reactions and also the photolysis of nitro PAHs. So we knew that the C2-naphthalenes were potentially going to react with the NO3 radical and make significant amounts of dimethyl-nitronaphtalenes and ethyl-nitronaphtalenes, and that these could then photolyze to form quinones. So one of the tasks was to, in fact, do these reactions and see which dimethyl and ethyl-nitronaphtalenes they would produce. This is data from Los Angeles from January 2003. And what I'd like you to notice here is the 2 to 4 ring PAHs could all be in the gas phase, at least partially. These 5 or 6 ring PAHs are going to be exclusively particle associated. But if you notice, the more abundant ones are the more gas phase ones. So we have 1,600 nanograms per cubic meter of naphthalene in contrast to 0.8 nanograms per cubic meter of benzoate pyrene. So the ones that we decided to concentrate on in this contract were these more volatile, more abundant ones. So naphthalene, 1 and 2 ethyl naphthalene, and the 10 dimethyl naphthalenes, and 1 and 2 ethyl naphthalene, 1 and 2 methyl naphthalene, ethyl naphthalene, and also the most abundant 3-ring PAH, phenanthrene. So these are the project objectives. This is a slide that's several years old. This is exactly what I brought up here for the kickoff meeting. So our objectives then were to evaluate the potential for atmospheric reactions to contribute to the atmospheric PAH-quinone burden, assessing the formation of PAH-quinones from atmospheric reactions by the hydroxyl radical, nitrate radical, ozone, and studying naphthalene, alkylnaphthalenes, and phenanthrene, and identifying the dimethyl-nitronaphtalenes formed from the atmospheric reactions of selected dimethyl-naphthalenes, and we selected 1,617 dimethyl-naphthalene and 2,6 and 2,7 dimethyl-naphthalene because these are the most abundant dimethyl-naphthalenes. And then the idea was to nitrate them and then photolyze the nitro products and see if we could make quinones out of them. I'm not going to have time to go through a lot of the experimental details, so I'm just going to show you a number of the methods we use for product identification and some of the advantages, disadvantages of them. So we did a lot of the work using atmospheric pressure ionization mass spectrometry for product identification. This is an in situ technique. So here's our atmospheric chamber. The air is being pulled into our API mass spec. You get protonated molecular ions from the water clusters that are the ionizing agent. And it's a triple quad, so we could do MS-MS. So theoretically, you could separate isomers if you could get them to collisionally fragment differently. But in order to do this, you would have to have standards for comparison. But it's an excellent way to screen for polar products. So we use this technique to screen for quinones from our reactions. We did a lot of product identification using gas chromatography mass spectrometry, GCMS. We have quadrupole and ion trap instruments in the lab. These are low resolution, low mass resolution instruments. Electron impact is nice because it gives you characteristic fragmentation. Chemical ionization will give you molecular ions. So if you're trying to figure out what the molecular weight of the compound is, that's a good way to go. And negative mode chemical ionization is very, very sensitive to nitro PAHs. Additionally, we had Proton Nmr, and the 400 megahertz NMR was used to identify 39 dimethyl-nitronaphtalenes and ethyl-nitronaphtalenes, 2 side chain nitrated dimethyl-naphthalenes, and 3-methyl phthalide during this contract. We sampled the parent PAHs, the naphthalene, alkylnaphthalenes, and phenanthrene onto 10x cartridges, thermally desorbed them, and analyzed, quantified them by flame ionization detection. So here's our 10x cartridge down here. And so this is used to measure the amounts of reaction during the chamber. You have to calibrate it, but the nice thing about this is that you can predict what your calibration should be. We also sampled products for GCMS using solid phase microextraction, and this is a solid phase microextraction. I'm having trouble finding my mouse. Oh, there it is. Fiber, and if you see in this blow up, there's the fiber right there, and you just put it into the chamber, have the fan on, and pull it back out, and inject it into the GCMS. So you use different fibers for various volatility products, and if you want to do on-fiber derivatization for carbonyls, we use one particular fiber. And these would typically be used to sample the chamber contents post-reaction, and for this you definitely need to be able to calibrate. So part of the problem we have with a lot of these things is that you don't have standards of these things for calibration. Finally, we sampled the products using polyurethane foam plugs and filter puff combinations, using a high-vol filter to sample essentially the whole chamber volume. I think Roger will have a picture of the chambers for you, but there's 6 cubic meter chambers that we did most of these reaction in. Then we could take the puffs in the filter, extract it, fractionate by HPLC if necessary, analyze by GCMS. One of the interesting things we found out when we started doing this is that some particles will actually go through the puff. So we thought if we had a puff there, we would collect gases and particles. You collect gases, but some of the particles will actually go through the puff. So when you do this filter puff sampling, you have kind of an operational gas particle definition. Operational because there will be gases that may be artifactually absorbed onto the filter or onto particles on the filter, and you can also have particle absorbed species that while you're pulling the air through the sample can get desorbed, and these will be collected on the puffs. When you do this for ambient sampling, the puffs will collect the 3 and 4 ring PAHs and the 2 ring nitro PAHs. Okay, let me start with phenanthrene. Phenanthrene is the most abundant of the 3 ring PAHs. And we said we wanted to look at its reaction with the radical-initiated species and with ozone. So the first question is, how fast does it react? And this is data that we had from the literature. Some of it is our data, some are from other investigators. But you can notice if you assume a typical OH concentration listed down here, NO3 and ozone concentration, this is about 30 ppb. You get lifetimes due to reaction with the hydroxyl radical and the nitrate radical that are fairly short and quite similar, 4.3, 4.6 hours, whereas the ozone reaction is 41 days. Even if the ozone were at 300 ppb, which thankfully it doesn't get to be very often anymore, this would only go down to 4 days. So the ozone reaction is slow. Now, what are the products of these reactions? Oh, and I also wanted to mention that we've looked before to see if you can make nitrophenanthrenes from phenanthrene, and you don't make very many nitrophenanthrenes. So the route of going from a nitro PAH to a PAH-quinone is not going to be very important for phenanthrene. So we just have these 3 reactions to consider. So why are we interested in 9,10-phenanthrene-quinone? Well, it has a very favorable reduction potential to undergo that redox cycling in biological systems. And in fact, in aerobic yeast systems, it's been shown that the 9,10-phenanthrene-quinone exerts its toxicity through reactive oxygen species. It's been found in diesel and ambient particles, and it's been found at elevated concentrations at what was considered downwind sites. So there's some indication that maybe it's formed in the atmosphere. And it has been postulated to play a role in the pulmonary toxicity of diesel particles. It's also been observed in ambient air at concentrations up to a nanogram per cubic meter, and it was responsible for the majority of the reactive oxygen species generation from extracts of ambient air from Fresno, California. This is some work by Chung et al., 2006 in ES&T. So 9,10-phenanthrene-quinone is an important quinone in ambient and diesel particles. So as I said, phenanthrene is the most abundant gas phase 3 ring pH in ambient air. And if you react phenanthrene with the hydroxyl radical, what you get is 2,2' diformal biphenyl and a little bit of phenanthrene-quinone product as well. If you react with ozone, this 9,10 double bond, which I've shown here in red, is the most reactive site. And using our API-MS, pretty much the only thing we saw was a secondary ozonide and a very small amount of the 9,10-phenanthrene-quinone. However, when we did the NO3 radical-initiated reaction, we got a significant yield, and measured by API, we found a significant 9,10-phenanthrene-quinone peak. So at that point, we decided to collect the chamber volume onto puff and filter samples, extracted it, ran HPLC, and did GCMS, calibrated everything with a standard of 9,10-phenanthrene-quinone, and we determined that we had produced a yield of 33% of 9,10-phenanthrene-quinone by this NO3 radical-initiated reaction. So if I call that 1 and just look at the relative amounts of the product that we found doing SPEME sampling in the other reactions, it would be about 0.1 for the OH radical reaction, so maybe a 3% yield and a little bit smaller yields for the ozone reaction. So if we want to calculate how much 9,10-phenanthrene-quinone these reactions are going to make in ambient air, we can do this assuming a typical phenanthrene concentration. Here I've used 10 nanograms per cubic meter. Typical OH radical concentration of 2 × 10⁶, NO3 5 × 10⁸, and our 30 ppb of ozone. So the yield of 9,10-phenanthrene-quinone is just going to be the rate constant. Sorry, I'm very challenged with this mouse here. The rate constant for the reaction times the reactant species, the hydroxyl radical, the time times the yield times the amount of phenanthrene. So for the OH radical initiated reaction, we get 80 picograms per cubic meter per hour. For the NO3 radical reaction, 800 picograms per cubic meter per hour. And for the ozone reaction, 0.2 picograms per cubic meter per hour. So we estimate that the NO3 radical initiated reaction is going to be the most important formation process for the 9,10-phenanthrene-quinone. I told you that when we first started this, people thought that maybe ozone reaction, and in particular in the adsorbed phase, might be a source of phenanthrene-quinone. We didn't do this, but Kahan et al. Studied, in fact, the lifetime of phenanthrene in an organic film exposed to 50 ppb of ozone, and it was 44 days. So the ozone reaction in the gas phase we found to be slow. The ozone reaction in the adsorbed phase is also slow. So it looks like the NO3 radical initiated reaction is the most important formation, but also the OH radical initiated reaction. So for future research, we would recommend that ambient measurements should be made for the 9,10-phenanthrene-quinone to assess the importance of the NO3 radical initiated formation pathways. And since certain nitro pHs and nitro pH ratios are indicators of NO3 chemistry, and I'm going to show you some of those a bit later, nitro pHs should also be measured. So there should be certain nitro pHs or nitro pH ratios that should show up simultaneous with elevated levels of the phenanthrene-quinone if they've been formed by the NO3 radical. And then, of course, there should be health effects studies designed to address the importance of nighttime NO3 chemistry. An optimum study would have measurements of the nitrate radical, the nitro pHs, 9,10-phenanthrene-quinone, and other quinones. And then you would want some kind of an appropriate bioassay or biological exposure to go along with that. Moving on to naphthalene and the alkylnaphthalenes. The first thing to look at is their lifetimes due to the OH or NO3 radical initiated reactions or ozone. And here I have what I've called extreme NO3. So you remember in the other slide, phenanthrene was 4.1 hours, and here I've got it down to 28 minutes because I've used 10 times as much NO3 radicals and also 100 ppb of NO2, which plays a role for the naphthalene and the alkylnaphthalenes. So you can see that the major loss process is, in fact, the OH radical initiated reaction. But that some of the NO3 reactions are starting to get pretty fast. Some as short as the lifetime is as short as 1 hour for some of the dimethyl-naphthalenes. The ozone reactions are pretty slow. So we did chamber hydroxyl radical initiated reactions of naphthalene, 1 and 2 methyl naphthalenes, 10 dimethyl-naphthalenes, and 1 and 2 ethyl naphthalenes, and here they all are. And I'm going to be talking about an alpha carbon and a beta carbon. So that's just the 1 carbon and the 2 carbons. So here we have the alpha naphthalene and the beta naphthalene. So we did this whole series of reactions using the API-MS to look for quinones, and we found quinones were really minor. So that was the first part of what we were supposed to do. We didn't find very many quinones, but then we decided to look at what we did find. And the API-MS analyses showed that the major products were ring-open dicarbonyls that are 32 mass units above the parent. There were also ring-open dicarbonyls of lower molecular weights that came from a loss of the 2 beta carbons and associated alkyl groups, and ring-containing products that seemed to be epoxides. When we did solid-phase microextraction analyses and GCMS analyses after the chamber reaction was done and took long-time samples, we saw the first 3, and in addition we saw anhydride secondary products. So these we think might be a potential source for the phthalic acids that people find in secondary organic aerosols, and that they've suggested in fact as markers of secondary organic aerosols. So the anhydrides were shown to be secondary in the naphthalene system, and the ring-open dicarbonyls are shown to be at least partially primary in the naphthalene system. So that's what I'm showing you here. This is a chamber reaction of naphthalene plus the OH radical. The little dots are our data points from our API-MS. The lines are from the model fit. So molecular weight 160, this is our ring-open dicarbonyl, 32 mass units above naphthalene, the 2-formyl cinnamaldehyde. Here's our loss of 2 carbons giving us phthaldialdehyde, a molecular weight of 34, and phthalic acid anhydride. So you can see the solid lines are the assuming a first generation product, and it looks like the 160 product is in fact first generation. However, if you look at the phthaldialdehyde, it doesn't really look like first generation. The dashed line is second generation, looks like something in between. So it's probably partially first generation, but in addition, you may be able to go from this to that, in fact. However, if you look at the phthalic anhydride, sorry, I have that wrong. No, this is the phthalic anhydride. It is second generation formed from first generation phthaldialdehyde. This is the phthaldialdehyde. If you assume that's first generation and then goes on to form this phthalic acid anhydride, we get this nice fit that matches the data here. Okay. Of course, in order to be able to do this, we had to look at the atmospheric chemistry of the phthaldialdehyde, and additionally, we had to know how much of the phthalic acid anhydride product it was producing. So we had to do some other chemistry so that we could do this modeling. So if we start with our naphthalene, this is the two products, the ring-opened dicarbonyl and the loss of the two beta carbons would happen here. These are our two beta carbons. So in fact, we could get phthaldialdehyde as a product from naphthalene, 2-methylnaphthalene, 2-ethylnaphthalene, and 2,3-dimethylnaphthalene. As I said, this could be formed. This is also very reactive, and it can, in fact, form phthaldialdehyde. And when we studied phthaldialdehyde, we found that the OH radical initiated reaction gave phthalic anhydride. Photolysis of phthaldialdehyde gave the phthalide and the phthalic anhydride. And under ambient conditions, probably the photolysis is going to win out over the OH radical initiated reaction. So in terms of the four products that I had listed on the previous slide, this is our number 1, parent plus molecular weight 32. This is number 2. After loss of two beta carbons, we get phthaldialdehyde. Number 3 were epoxides, and here's a structure that we proposed for the epoxide from naphthalene. Number 4 was secondary products, and these were suggested to be phthalic acid, precursors of phthalic acid that are markers of SOA. I should point out that for the naphthalene, we also did naphthalene fully deuterated and 1 and 2-methylnaphthalene fully deuterated. And because we had the deuteration, we were able to see that everything was consistent with the structure that we have here, because you get hydrogen exchange of the OD here if you start with the deuterated compound. So by the molecular weight that we got, we were able to see that it was consistent with it being, in fact, a hydroxy-epoxy ketone. The molecular weight 148 species resulting from loss of two beta carbons from the methylnaphthalenes and two beta carbons and associated alkyl groups from the dimethylnaphthalenes. So we had a standard of 2-acetylbenzaldehyde. I should point out that that was, as I said, I guess one of the problems was that we didn't have standards of a lot of these products, but we did have a standard of 2-acetylbenzaldehyde, so we could confirm that this was in fact the product of the 1-methylnaphthalene, 1,2, and 1,3-dimethylnaphthalene. The other thing I wanted to point out is if just looking at the 148 products, the major product, of course, was just the ring-open product, 32 mass units above the parent, but in terms of the ones losing the beta carbon, 86% of it was for reaction on the substituted ring. If you start with reaction on the substituted ring, you get the 2-acetylbenzaldehyde. In order to get this compound, you have to start with the OH attacking the ring that does not have the methyl substitution. Okay, so this suggests that the OH preferentially attacks the substituted ring. The dicarbonyl products are generally consistent with the OH radical adding preferentially to the position ortho to the alkyl substitution. However, when we looked at the products of 1,2-dimethylnaphthalene, it was consistent with a ring opening between C1 and C2 right here. And the only way we could make the product was if we had an ipso addition to the OH ring. Ipso meaning going to the position where the methyl is already at, so like this. And we only got one molecular weight 188 product out of 1,2-dimethylnaphthalene. Some of the isomers gave many molecular weight 188 products. But based on the MS fragmentation, we are suggesting that this is the structure. We had a standard of 2-acetylbenzaldehyde, so we could prove that that was the ring opened with loss of beta carbons was giving us 2-acetylbenzaldehyde. So we think that it is, in fact, an ipso addition. So recommendations for future research, we really identified a suite of oxygenated compounds from the OH radically initiated reaction of the alkylnaphthalenes. And we should look for these products in ambient air, as well as what is their toxicity should be determined. These products include reactive unsaturated dicarbonyls and epoxides. Additionally, when you have that loss of 2 beta carbons, you end up forming glyoxyl, methyl glyoxyl, or biacetyl as the expected co-products from that reaction. Another recommendation that I should have put here is I think it would be very important to go ahead and produce enough of these products so that an NMR identification could be done on them, either by doing the reaction and just simply collecting enough or doing a special synthesis for it, because it would be nice to be able to confirm the exact identity of these products, and for that you need to characterize them by NMR. So the identifications by the GCMS should be viewed as tentative. Okay, then the next way we might form quinones was from the NO3 radical initiated reactions. So again, we went and did the reactions of the naphthalene 1 and 2 dimethyl-naphthalene, 1 and 2 ethyl naphthalene, well, all those compounds again. Here they all are. Okay, so we wanted to assess the formation of quinones and nitro products and see which of these nitro products then might photolyze to form quinones. So these are the same isomers for the OH radical initiated reaction, just for variety. I've shown them in the order that they elute from a 5% phenylmethyl-siloxane column. We haven't found any one column that will separate these 15 compounds. You need to use 2 different columns to separate them, or maybe GC by GC is the way to go for this. Okay, so why are we interested in nitro PAHs? I just want to quickly review that. They are genotoxic and carcinogenic. So if you look at the certain nitro PAHs that have been found in diesel particles compared to the ones that have been found in ambient air, you find 1 nitropyrene, whereas in ambient air you find 2 nitrofuranthene and 2 nitropyrenes, isomers, but different from the electrophilic nitration product. When bacterial assays have been done, these have all been positive. When human cell assays have been done, these have been positive. And when animal carcinogen assays have been done, these have all been positive. There are fewer crosses here, I think mainly because the atmospheric reaction products haven't been studied as much. So I think the bottom line is that nitro PAHs are probably human carcinogens. At least that was the conclusion of the International Panel on Chemical Safety. So we have gas-phase PAH, particle-associated PAHs. So I said before, you can have OH radical reaction during the daytime, NO3 radical reaction at nighttime. These are the particle-associated things. These can all produce nitro PAHs. Now, but you'll get different nitro PAHs. So let's use furanthene for an example. If you react it with the hydroxyl radical, you get 2 nitrofuranthene with a 3% yield. If you do the reaction with the NO3 radical, you get 2 nitrofuranthene with a higher yield, 24%. If it's formed by some sort of a heterogeneous reaction on the particle phase, you get the electrophilic nitration product, 3 nitrofuranthene. So you can distinguish these radical initiated reactions from electrophilic nitration. For pyrene, the hydroxyl radical gives 2 nitropyrene. Pyrene plus the NO3 radical does not produce a nitropyrene. And the electrophilic nitration product of pyrene is what you find in diesel exhaust is 1 nitropyrene. And of course, you can get oxy PAHs from these different ways that I showed you, that I mentioned before. So the nitro PAHs that you find in ambient particles are in fact dominated by isomers formed in the atmosphere from the gas phase reaction. So if we start out looking at diesel particles, you find mainly 1 nitropyrene. If you had a good sample and you analyzed it really hard, you might find a little bit of 3 nitrofuranthene in there, but no 2 nitrofuranthene. However, if you do an OH radical reaction in a chamber, you produce 2 nitrofuranthene, 2 nitropyrene. If you look at the daytime sample from Torrance, California, it presumably has undergone hydroxyl radical initiated chemistry, and you find 2 nitrofuranthene and 2 nitropyrene in the ambient sample. If you look at a nighttime sample from Claremont, California, you find a huge 2 nitrofuranthene peak, very small 2 nitropyrene peak, and 1 nitropyrene peak. So the 1 nitropyrene presumably is from a direct emissions. The 2 nitropyrene presumably was made from the hydroxyl radical initiated reaction during the day, and at night we formed a huge amount of 2 nitrofuranthenes. So NO3 radical initiated chemistry was happening at night at that downwind site in Claremont. But the point is that you can have gas phase radical initiated reactions, and they lead to less volatile particle associated products. Okay, so the ratio of the 2 nitrofuranthenes to 2 nitropyrene can then indicate what kind of chemistry has occurred. So we looked at some samples in Mexico City. The 2 nitrofuranthene to 2 nitropyrene ratio was always less than 10, which is what you see in the chamber if you do an OH radical initiated reaction of furanthene and pyrene. You get about a 10-to-1 ratio of 2 nitrofuranthene to 2 nitropyrene. On the other hand, in the samples from Southern California, notice my axis here is 120. So the very large ratio of the 2-nitrofluoranthene to 2-nitropyrene suggests NO3 radical initiated formation of 2-nitrofluoranthene. Southern California NO3 chemistry is important. One thing that really surprised us here is we saw this NO3 chemistry in Riverside. This is University of Southern California. This is UC Riverside. So we're to the east of USC. We're downwind. So we kind of expected that at a downwind site at night we might see NO3 reactions. What surprised us is there seems to be some evidence for NO3 reaction even at what we thought was the source site at USC. So perhaps this was going on at higher elevations. At ground level at USC, there's always so much NO coming out of traffic, you wouldn't expect to have any NO3 chemistry. But as you get at elevated layers, you might have the NO3 away from the NO2, and you can get NO3 chemistry occurring that way. So this is another example that there's NO3 chemistry can occur in Southern California. These are the methyl nitronaphthalene. These are GCMS traces of the 14 isomers of the methyl nitronaphthalene. And the two that we see in Azusa that I've marked, 1-methyl-5-nitronaphthalene, 1-methyl-4-nitronaphthalene, are what you get in a chamber reaction of 1 and 2-methyl-naphthalene exposed to OH radical initiated reactions. So these are signs of hydroxyl radical chemistry. And as you go to Riverside and further downwind to Banning, you see that these peaks that I've shown here in red are growing in, and these are in fact markers of NO3 chemistry. So if we do a chamber reaction of 1 and 2-methyl-naphthalene with the NO3 radical, we find mainly 2-methyl-4-nitronaphthalene. What I want to point out is these are all nighttime samples. So if you're only looking at nighttime samples, if you only have hydroxyl radical chemistry occurring during the day, and nothing happening at night, then your daytime and nighttime samples are going to look the same because what you're seeing at night was made during the day. And that's in fact the case. If you look at this sample at Azusa, the daytime one looks just like the nighttime one. And the other place that we saw this is Mexico City. So I'm going to show you, I've shown you a number of ambient samples, and the message to remember is in Mexico City and Azusa, it looked like hydroxyl radical initiated reactions. Downwind sites in Southern California, it seemed like we were getting NO3 chemistry occurring. Okay, this again is from our kickoff meeting. Task 4 was to conduct the synthesis of the dimethyl-nitronaphthalene. We're going to do this in solution with N2O5 and CCl4, and we expected to get the same isomers that we get from the NO3 radical initiated reaction in the gas phase. As I mentioned, we chose the 4 most abundant. We were going to do 1,6, 1,7, 2,6, and 2,7. And try to synthesize enough of the dimethyl-nitronaphthalene so we could do some photolysis to see if the photolysis would make quinones. So once we got started, we kept going. So we conducted the nitrations of N2O5 and CCl4 for all 10 dimethylnaphthalenes and the 2 ethylnaphthalenes. And we were able to report the EI mass spectra and retention industries of 42 dimethylnitronaphthalenes. That's all that there are. And we had NMR characterization of 32 of them. And 11 of the 14 ethyl nitronaphthalenes, we could report the retention indices. 3 of the assignments were tentative, and we had NMR characterization of 7 of these. So the dimethylnaphthalenes, because of the symmetry, you either get 3 possible isomers or 6 possible isomers. So often it was the case, for instance, if you get 3 isomers, that when you did this reaction in solution, you'd produce enough of 2 of the isomers that you could get the NMR, and therefore the 3rd isomer had to be the missing product. So by playing games on many weekends with these NMRs, we were able to figure out what was what. So in fact, I'll show you a little bit of this. The 42 dimethylnitronaphthalenes can be divided into 6 groups with characteristic EI mass spectral fragmentation, retention behavior on the GC, and characteristic chemical shifts influenced by the protons that are next to the, oh, goodness, the NO2 group. I just went to the end because I hit the wrong thing. Sorry, very sorry. Okay, so here I am, sorry. Okay, so the first group is dimethylnitronaphthalene isomers with NO2 substitution on an alpha carbon and no steric interaction with the methyl substituents. Here's an example here. And notice that the shift of the proton peri to the NO2 group or ortho to the NO2 group, this is ortho, this is peri, is quite large, between 0.6 and 0.9. The second class would be dimethylnitronaphthalene isomers with the NO2 and methyl groups in peri position. And notice now that the shift of the proton ortho to the NO2 is quite small. The third class, dimethyl-nitronaphtalenes with NO2 substitution on an alpha carbon and an orthomethyl group. Here, the periproton is actually shifted upfield. Dimethyl-nitronaphtalenes with NO2 substitution on a beta carbon and no steric interaction. And notice how nice these big shifts are from the ortho and position, 0.7 and 0.9. Dimethyl-nitronaphthalene isomers with NO2 substitution on the beta carbon and an orthomethyl group also on a beta carbon. And finally, dimethyl-nitronaphthalene isomers with NO2 substitution on a beta carbon and an orthomethyl group on an alpha carbon. So NO2 on a beta ortho methyl group. And here the shift of the ortho proton is less. So the other thing that I mentioned that we use for identifying these things are retention indices. I just want to define what a retention indice is. So here the black is the nitronaphthalenes. It's the select ion monitoring analysis for MOZ 173. That's the molecular ion of the nitronaphthalenes. This is 1 nitronaphthalene, 2 nitronaphthalene. So if I assign the retention indice of 1 nitronaphthalene as 200, and I assign the retention indice of 9 nitrophenanthrene as 223, which is molecular weight 223 as 300. So 200 for 1 nitronaphthalene, 300 for 9 nitrophenanthrene, and then just interpolate in between. So if a dimethyl nitronaphthalene comes out halfway between these things, then its retention indice is 250. And this is done on a GC column that has to have a linear temperature program. Okay. So for the dimethyl nitronaphthalenes with NO2 and methyl substitutions in the peri position, and I'm not going to go all 6 classes, I'll at least show you a couple of them. So here we have peri position NO2 and methyl group. You see that there's a characteristic fragmentation pattern, M minus OH. So this loss of an OH is very characteristic. In fact, it's the base peak. But the other thing to notice is that all 6 of these different isomers, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and 1, 7, dimethyl 8 nitro have remarkably similar EI spectra. The NO2 group is in fact anisotropic, which means that the electron density around the C-NO2 bond isn't symmetric. So if you have the NO2 and the methyl groups peri to one another, the NO2 is crowded. It will be twisted out of the plane of the naphthalene ring. And the result of that is that you get a very small downfield shift of the ortho protons, which you can see here, only about 0.1. These peri-substituted isomers also will elute early because of this interaction between on their GC column between the nitro and the methyl groups. So for example, 1,2-dimethyl 8 elutes first of the 6 possible 1,2-dimethyl nitronaphthalene isomers. So dimethyl nitronaphthalene isomers with NO2 substitution on an alpha carbon and an orthomethyl group. Here again we have an M-OH fragment, but it's very small in this case. The chemical shift of the proton peri position is actually upfield, and again the interaction of the ortho, nitro, and methyl makes the molecule less polar, and it's early eluting. So the 2,7-dimethyl-1 elutes first of the 3 possible 2,7-dimethyl nitronaphthalene isomers. And this is the last one I'm going to show you, is NO2 on a beta carbon and no steric interaction. Note that you get a really nice molecular ion. It's the base peak of the spectra. And notice again how similar all the spectra look. It's uncrowded, so you get large downfield shifts, 0.7, 0.9. And consistent with the fact that 2-nitronaphthalene would elute after 1 nitronaphthalene, each of these isomers elutes last of the isomers from a given parent. So for example, this 1,6-dimethyl 3-nitronaphthalene elutes last of all the 1,6-dimethyl nitronaphthalene isomers. Okay, so the amounts that we actually managed to make of these dimethyl nitronaphthalenes as crystals are shown here. So we got a whopping 200 milligrams of 2,6-dimethyl 1-nitronaphthalene by doing several nitrations, and smaller amounts of the others. So we had the retention indices in mass spectra sufficient to identify all of the isomers produced from the NO3 and the OH radical-initiated reactions. And but for ambient analyses, many of these were going to collude because they had the same retention indices. So we started out by photolyzing the one that we had the most of, the 2,6-dimethyl 1-nitronaphthalene, and it did in fact give us 2,6-dimethyl-1,4-naphthaquinone. It didn't seem like a very high yield, so we went back to one that we'd done before, 2-methyl-1-nitronaphthalene, to get 2-methyl-1,4-naphthaquinone, as we'd done previously. But we found that we had a very low yield if we measured this in the absence of NOx. So then we studied it at different NOx concentrations, and this is what we found, that the yield seemed to be dependent on the NOx concentration. If we had just a little bit of NO2 in there, you got a yield more like what we had expected, the 18% we'd seen earlier. So this NOx dependence was really surprising. We thought, oh, maybe it's some kind of a chamber artifact. And that's where we are now, thinking it's a chamber artifact, because when we did reactions of the dimethyl-naphthalenes with the NO3 radical at low NOx concentrations in the MTC, which is one of our Teflon chambers, we got different results than if we did it in the ITC, which is another one of our Teflon chambers. And additionally, if we were in the MTC, where all of these reactions that were a function of NOx were done, we got more of a heterogeneous side chain product that I'm going to discuss below. That was very high in the MTC. So we think that there was something going on, and we were getting having very strange wall effects in the MTC. So we finished up our reactions in the ITC, and basically we recommend that this needs to be, additional experiments need to be done to look at the photolysis, because we don't think it should be a function of NO2. Okay, so task number 3 had been to identify the dimethyl-nitronaphthalene, as I mentioned, from the formed from the OH and NO3 radical initiated reactions of the 4 most abundant dimethyl-naphthalenes. We did the OH radical initiated reactions of 1,6, 1,7, 2,6, and 2,7. We found very low yields of dimethyl-nitronaphtalenes. We didn't quantify them because they were so low, but we thought maybe it would be better to find out what the profile is, so that we could compare the profile with what we would see in ambient air, the way we've done with the methyl-nitronaphthalene. So we made a surrogate mixture of all of the dimethyl-naphthalenes, as you would find them in ambient air, and reacted them with the OH radical, and also reacting with the NO3 radical. And then we went back and did the NO3 radical reactions and measured the yields of the nitro isomers for all 10 of the dimethylnaphthalenes and 1 and 2 ethylnaphthalene. And these yields were determined by GCFID, and additionally, we measured yields of the quinones. So we did find, in the NO3 radical initiated reaction, we found quinones as well as nitros in high yield. From the OH radical initiated reaction, we found very little quinones and very little nitros, in fact. Okay. So this is our NO3 radical initiated reaction of the surrogate mixture. This is the surrogate mixture, so we had more of the 2-ethyl and the 2,6 and 2,7 dimethylnaphthalene in the mixture. These are proportional to what you find in ambient, and if you mix them all together and react them with the NO3 radical, this is the pattern of the nitro isomers that you find. This is done by GCMS with NCI, negative chemical ionization. It's very sensitive. We were able to sample these just using a SPME for 5 minutes after the reaction was done, and doing GCMS analysis on it. And you can see that we made many isomers. Let me just point out 2. We made the 2,6-dimethyl-1-nitronaphthalene and the 2,6-dimethyl-4-nitronaphthalene. Notice that this is labeled as 8% and this is labeled as 6%. And the yields were measured, as I said, by the FID. And the reason that this is looks like a smaller peak here is because the NCI has very selective sensitivity. So you really have to calibrate the NCI if you're going to know how much of a particular nitroisomer you're forming. So here we have again the surrogate mixture reacted with the NO3 radical. This is the pattern of the dimethyl-nitronaphthalenes, and what I'm showing, comparing it to, is in fact an HPL fraction of a nighttime puff sample from Redlands, California. So this is an actual ambient sample. Redlands as downwind of Riverside, downwind of LA, and you can see, especially in the early part of this chromatogram, they look remarkably similar. Where they start changing, in fact, right here, this is in fact the highest isomer that's found in the OH radical initiated reaction. So let me show you the OH radical initiated reaction. So this is our surrogate mixture reacted with the OH radical. And this is a Mexico City morning puff sample HPLC fraction. So as I said, Mexico City looks like OH radical initiated chemistry. Redlands and other places in Southern California look like nighttime NO3 chemistry. I can label these as 1,6-dimethyl-5 co-eluting with 1,6-dimethyl-2 because each of these were done individually. And these are other isomers that, based on the retention indices, they could only be these particular isomers that I've labeled. So we had previously published a paper where we had done a diesel fraction with the hydroxyl radical. And in that chromatogram from the OH radical-initiated reactions, we had some early peaks. What we've now discovered is that those early peaks had to have been artifacts, because this is, in fact, what we now get when we do it much more carefully and we sample with a spiny that's going to be less likely to have artifacts. We get nothing in the earlier portion of the chromatogram. So then, looking at this Mexico City sample, we have some things in the early portion of the chromatogram. So this could either mean that there was some NO3 chemistry, which is what I kind of think is the case, but at this point I'm not willing to rule out the fact that there could have been electrophilic nitration during sampling, because these are also the electrophilic nitration products that you would get. So in Mexico City, there would be a lot of NO2 nitric acid. Maybe some of this was formed artifactually, or there was a little bit of NO3 chemistry. So this is something we need to find out for sure. So the yields of the dimethyl and ethyl nitronaphtalenes from the OH radical reactions are small. What we find instead is these ring-open dicarbonyls. So here we have a mechanism, the OH radical adding postulated mechanism, speculated mechanism. The OH radical adding to the position of highest electron density next to the methyl group. And you'll notice I then have it reaction with NO2 rather than O2, which is maybe surprising to some of you atmospheric chemists, if there are any in the audience. And, well, there are, I see some. But Roger's going to discuss why we think this is, in fact, happening with NO2. And also, NO2 has to be involved in forming the ring-open dialdehyde after loss of 2 carbons. If we want to make a nitro, we could put the NO2, the hydroxyl radical here, add the NO2 ortho. A loss of water would give you the most abundant nitro dimethyl-naphthalene that we find. And as I said, the yield of this is quite low. So from the OH radical initiated reaction, ring-open dialdehydes are greater than dialdehydes with loss of 2 beta carbons. And these are both greater than the dimethyl nitronaphtalenes. And the NO2 dependence will be discussed in the next talk. For the NO3 radical initiated reactions, the mechanism that we have postulated is that the NO3 radical adds to the position of highest electron density, shown here, and then that the NO2 adds peri, and that you have a loss of nitric acid across the ring, which you wouldn't expect to get from the OH radical initiated reaction, because you'd be trying to lose water, and here we're trying to lose HNO3 across this ring. And this seems to give the right proportion, or the right isomers that we find to be the most abundant. And we, in fact, found 15% of 2,7,4 and 5% of 2,7,1 nitro dimethylnaphthalene. We also found quinones. We could envision the quinone mechanism as after the NO3 radical adds to the position of highest electron density. If we get a decomposition, we get a radical species, then reacting with NO2, we somehow end up with a quinone. So we're currently studying these reactions as a function of NO2, and these yields that I've shown are for 1 ppm of NO2, but we've done enough things now that we can, I think, say with confidence that even under ambient NO2 concentrations, you're going to be forming the dimethyl nitronaphtalenes from these NO3 reactions, and that's consistent with the fact that we, in fact, find them in ambient air. So in terms of the quinones that can be formed from the NO3 radical initiated reactions, you get higher yields if the alkyl groups are on the beta carbon. So for example, here we have 2 alkyl groups on beta carbons and from 2,3-dimethylnaphthalene, and we get a 4% yield of 2,3-dimethyl-1,4-naphthaquinone. If we have only 1 beta methyl substituent, we get 2.2 and 3.9% yields. A little bit less if we just have the one on one side. And let's just look at the ethyl nitronaphthalene. So if we have the reaction occurring on the substituted ring, we get 1.8% of the quinone. If we have the reaction occurring on the unsubstituted ring, we only get 4% of the quinone. So nitration of the alkyl group was seen for 1,2-dimethylnaphthalene, 1,4-dimethylnaphthalene, 1,8, and 1,3. Now this is that side train nitration that I alluded to that made us think that strange things were happening in our chamber walls. And this is what I mean by side chain nitration. In fact, you get CH2NO2. And if I look at the ratio of this form to the most abundant dimethyl nitronaphthalene made from 1,2-dimethylnaphthalene, the ratio changes dramatically depending on the chamber. If I look at the ratio of the two nitros that are formed, it's pretty constant. So the relative yield of the side chain nitro to the most abundant nitro varies by a factor of 30 between the two chambers. It's just going from one Teflon chamber to a similarly identical Teflon chamber. So this suggests that the side chain nitration is heterogeneous and that the MTC may have had wall problems. So this is why we think that perhaps this was also what was going on when we were finding a NOx dependent of our photolysis. So in terms of the mechanism to get the most abundant isomer from nitro isomer from the 1,2-dimethylnaphthalene, we can again suggest an ipso addition of the NO3 radical, adding the NO2 across the ring and losing nitric acid, and that gives you, in fact, the most abundant isomer, 1,2-dimethyl-4-nitronaphthalene. So questions remain regarding the mechanisms following the initial addition of the OH and NO3 radicals to naphthalene and the alkylnaphthalenes. The ipso addition is something that's very interesting that should be investigated further. The apparent NOx dependence of the quinone yields from the photolysis of the alkylnaphthalenes needs to be assessed. Ambient measurements of quinones should be made at upwind and downwind sites and locations where NO3 radical chemistry is likely and unlikely to occur in order to evaluate the importance of these atmospheric formations. And this would confirm our laboratory chamber data with ambient observations. And finally, I think the potential for artifactual formation of the dimethyl nitronaphthalines during ambient sampling should be evaluated. So these are the papers that have resulted from this contract. And you can look them up at your leisure. And these are the people who did the work. I want to, you'll notice that most of these papers, the first author is L. Wang. This is L. Wang, this very tall guy here. And he just got his PhD and is going on to do a postdoc last week. And Katie Gallagher is the woman who did all the nitrations in solution. And of course, Bill Harger and Sarah Ashman were also helping us out. So I'll take any questions.
Well, to start out with, we do have a question off the web from Beth Schwer at ARB. Are any of these toxic quinone and related compounds known to be associated with jet engine exhaust, like you mentioned they are with diesel engine exhaust? Overall, are there implications from your work for attributing additional toxicity to jet engine exhaust beyond the current way of attributing the toxicity to jet exhaust based primarily on gaseous VOC species and filter-based metal species only?
Okay, I don't know if anybody has looked for quinones from jet engine exhaust. Since you find them in diesel exhaust, I suspect there might be some there. In terms of additional toxicity, I think if you will get PAHs in jet engine exhaust, and any PAH, once it gets into the atmosphere, can form these other, through the atmospheric reactions, can form these other toxic species. So yeah, I think just measuring the primary things coming out of any exhaust is missing whatever happens in the atmosphere to form, especially if you have any PAHs coming out of your exhaust, then you need to consider the atmospheric reactions if you're going to consider the toxicity of the exhaust.
Yeah, I might just add a word or two on that, since I've been managing a jet engine exhaust, well, really an airport study, but with work at the blast fence at LAX. We had a PAH component to that, and we really didn't find as high levels of PAHs as we had expected. And I think it is true that jet fuel, like diesel fuel, has a lot of PAH in it, a few percent. I'd say in general, jet engines certainly when they're taking off, there's a major throughput of the fuel. There's a high level of combustion. You seem to get PHs more from idling conditions or when there's less air going through the engine. In terms of quinones, there hasn't been any work, to my knowledge, done in that area. But just in general for the PAHs, the levels weren't as high as we might have expected based upon the similarity in the fuel and the fact that diesel exhaust, we get a lot of PAHs in the exhaust.
So it's not good for the atmosphere or for people to have your jet engines idling.
No,
Okay.
no, not if they're idling. Any questions from the audience here?
Well,
Why do you think you didn't see any nitrate chemistry in Mexico City? Is it, you think maybe seasonality, or close, if you look downwind, or?
well, Mexico City is, it has very intense traffic, just like LA, and it's kind of in a bowl. So it has a lot of PAHs, has a lot of the starting materials, and in fact, the OH chemistry starts up really early in the morning there. They have really high OH levels just shortly after sunset, and but at night things kind of clear out. So as long as you have NO from the cars titrating out your ozone or your NO3 radical, you're not going to have any NO3 radicals. So I think it's more the meteorology of the system rather than the emissions. I think the same emissions are there as in LA, but where at night everything kind of gets blown out and through this hole in the gap in the bowl, everything exits out, that you don't get the same kind of chemistry that we have when things kind of slosh around in the basin, sometimes even going back and forth. So you might. That was something I wanted to do, but we weren't able to.
Any other questions? Well, thank you very much, Janet. We appreciate.
Announce the 5-minute break.
Oh yeah, we're going to have a 5-minute break so we can get ready for the next presentation by Dr. Atkinson.